Have you ever really stopped to think about how your body just knows? How it knows exactly how much water to hang on to and how much to get rid of? Well, it's this incredible non-stop balancing act happening inside of you right this very second. So let's dive into the fascinating world of osmoregulation, your body's master system for managing water.
You know, when it comes right down to it, it's all about your cells. I mean, think about it. If you have too little water, your cells start to shrivel up. But if you have too much, they can actually swell and even burst. This is the fundamental problem your body has to solve every single second just to keep you alive and kicking.
And the official name for that solution is osmoregulation. It's just the biological process of keeping the fluid inside and outside your cells in this perfect, delicate harmony. It makes sure the concentration of stuff like salt and sugar in your blood stays within an incredibly tight, safe range.
So who's the star player in this whole game? Well, it's your kidneys. These amazing organs are basically the command center for maintaining that perfect fluid balance. And trust me, they do way more than just filter out waste.
Okay, to really get how the kidneys pull off this balancing act, we first have to appreciate the sheer scale of their operation. We're going to start by looking at their main job, filtration. And the amount they filter every day, it is truly mind-boggling.
So let's zoom in a bit. The real work is done by about 1 million tiny microscopic powerhouses in each kidney. They're called nephrons. You can think of them like individual water treatment plants, all working together, all at the same time.
All right, get ready for this number. Every single day, your kidneys filter a staggering 180 liters of fluid out of your blood. That is the equivalent of 90 of those big 2-liter soda bottles. Your entire blood supply gets filtered something like 60 times a day. It's just wild.
But hold on. Think about that number. We obviously don't pee out 180 liters a day, right? We only produce about 1 to 2 liters of urine. So what does that mean? It means our kidneys have to reclaim over 99% of all the fluid they just filtered. This incredible act of recovery, that's where the real magic of osmoregulation truly begins.
So how does that first filtration even happen? Well, it's a process called ultrafiltration. Basically, blood rushes into this little knot of capillaries, called a glomerulus, through a wide tube, but it has to leave through a much narrower one. This creates a ton of pressure, and that pressure literally forces all the small stuff, water, salts, glucose, urea, through this superfine 3-layer sieve, while keeping the big things, like blood cells and proteins, behind.
Okay, so we've just chucked almost everything out of the blood. The nephron's next job is a massive recovery operation. We're calling it the Great Water Rescue. Let's see how this incredible mission to get back over 99% of that fluid actually works.
The rescue mission kicks off immediately right at the first stop in the pipeline. It's called the proximal convoluted tubule, or just the PCT. This part of the nephron is an absolute powerhouse of reabsorption. Right away, it grabs back about 2/3 of the water and sodium. And, super importantly, it reclaims 100% of the valuable nutrients, like glucose and amino acids. We do not want to lose that stuff.
So what's driving all of this? The real engine here is a little machine called the sodium-potassium pump. And this thing uses a ton of energy to actively pump sodium out of the tubule and back into the blood. This creates a powerful gradient that then pulls in even more sodium, and water and glucose just follow right along with it, back into the body where they belong.
Okay, so we've reclaimed the bulk of the good stuff. But how does the kidney make that critical decision? You know, the one to either save a ton of water by making concentrated urine or get rid of excess water with dilute urine. Well, the answer lies in the most ingenious part of the entire nephron.
Meet the loop of Henle. Now, this thing has 2 parallel limbs that do completely opposite things. As the fluid goes down one side, the descending limb, water gets pulled out because the walls are leaky to water. But then, as it goes up the other side, the ascending limb, salt is actively pumped out, but this side is totally waterproof.
This incredibly clever setup creates what's known as a counter-current multiplier. Here's how it works. That ascending limb is constantly pumping salt into the surrounding kidney tissue, called the medulla. This makes the medulla incredibly salty. In turn, that powerful saltiness passively pulls water out of the descending limb. And because the two tubes flow in opposite directions, the effect gets multiplied all the way down the loop, creating this massive salt gradient that is absolutely key for concentrating urine later on. It's brilliant.
So, the kidneys have now cleverly set up the potential to save a lot of water by building this salt gradient. But what makes the final call? What tells the kidney whether to actually save that water or just let it go? Well, that requires a signal from headquarters, a hormone that can give the final order.
And that plant manager is a hormone called ADH, or antidiuretic hormone. The name says it all. Antidiuretic literally means against producing urine. This hormone is the master regulator that gives your kidneys their marching orders: conserve water or let it go.
Now, the signal to release ADH comes from your hypothalamus, deep in your brain. It's constantly monitoring your blood's concentration, what scientists call osmolality. So if you're dehydrated and your blood is a bit too salty, high osmolality, your brain basically yells, release the ADH. But if you're well hydrated and your blood is dilute, it says, all right, stop the ADH. It is a perfect negative feedback loop, all designed to keep you in balance.
So what does ADH actually do? It travels through your blood all the way down to the final section of the kidney's pipeline, the collecting duct. And there it acts like a key. It unlocks a process that inserts these special little water channels, called aquaporins, into the walls of the duct. This suddenly makes the duct super leaky to water. Now, as the fluid passes through that super salty medulla we built earlier, tons of water rushes out and gets saved. So here's the bottom line, the crucial point. High levels of ADH mean more water channels, which means more water gets reabsorbed, and what you're left with is a small amount of concentrated urine. Low levels of ADH mean fewer water channels, so less water is reabsorbed, and you end up producing a large volume of clear, dilute urine. Your body is fine-tuning this system every single minute of the day.
This whole system is unbelievably precise and robust, just working silently in the background every second. But what happens when that balance is lost? Looking at what goes wrong is actually one of the best ways to appreciate just how critical this system is for our health. Normal dehydration and overhydration, that's just the system working exactly as it's supposed to. But in a condition like diabetes insipidus, there's a problem with ADH itself. Either the body doesn't make it, or the kidneys just can't respond to it. And the result? The collecting duct never gets leaky to water. This leads to the excretion of massive volumes of really dilute urine, which in turn causes extreme, unquenchable thirst.
So from a 180-liter filter to a hormonal control system that fine-tunes your water balance minute by minute, the nephron is truly a marvel of biological engineering. It works tirelessly, 24/7, just to keep your cells safe and sound. And that really leaves us with just one final thought. Knowing how incredibly hard this microscopic system works for you, what choices are you making to help it out?